Hi everyone, my name is ECE-GY. I'm gonna do the question 1 for Mock 10, so let's begin. Okay, so it is a pretty long question. It has to collect some definitions and simple properties like probability masses or density, mean, autocorrelation, and autocovariance functions of some stochastic processes it lists. So the first one will be the Poisson process. So the Poisson process actually comes from the Poisson random variables. So the number of some calls received in t hours equals to k will be equal to the minus lambda times t's power of e times the kth power of lambda times t over the fraction of k. So here, if the t is not fixed, and the number of calls received in t will be a function of both t and lambda. Will be of both t and this k, so it will be a stochastic process. So we will define the Poisson process xt as follows, like the probability of xt equals to k will equals to the minus lambda times t's power of e times the kth power of lambda times t over the fraction of k, and the expectation of the Poisson process and also the variance of the Poisson process are both lambda times t. It's a special properties. And the autocorrelation will equals to the lambda square times t1 times t2 plus lambda times the mean of t1 and t2. And the autocovariance will equal to the lambda times main mode of time t1 and t2. That is because the autocorrelation actually equal to the autocorrelation minus the expectation of xt1 and xt2. So actually all the autocorrelation in all these 7 stochastic process can be derived like this. And we know that the mean of Poisson process is lambda t, which is a linear function of t. So I feel it is reasonable because the longer time we wait, the expected number of buses is larger. Yeah. So the second will be a Poisson increment process. It is defined as yt equals to xt plus epsilon minus xt divided by epsilon, where xt is a Poisson process. So its first order probability masses will be probability of yt. It should be kept to 1. Equals to n over epsilon will be equal to the minus lambda times epsilon's power of e times the nth power of lambda times epsilon over the nth fraction. And the expectation of it will be equal to lambda, and the autocorrelation will be equal to lambda square when t1 minus t2's absolute value is larger or equal to epsilon, and when the t1 minus t2's absolute value is smaller than epsilon, the autocorrelation's value will be lambda square plus lambda over epsilon minus lambda times the absolute value of t1 minus t2 over the epsilon square. And the autocovariance will be equal to 0 when I will just say tau will be equal to the t1 minus t2, and the tau absolute value of tau will be larger or equal to epsilon, and when tau is smaller than epsilon, the result will be lambda over epsilon minus lambda times the absolute value of tau over epsilon square. So here actually we can say that it is actually a WSS process because the expectation of it is a lambda is a constant, and autocorrelation of it is just related to the tau, which is the T1 minus T2. And we will know that it is the expression of its autocorrelation is a triangle with area lambda, which is actually independent of lambda. Which is independent of epsilon. So, and when epsilon goes to 0, the triangle becomes an impulse with area lambda. And for the third, is Poisson impulse process. It is defined as Ct equals to dxt is over dt, where xt is a Poisson process. So it has no definition of probability masses actually, and expectation of it is also equals to lambda, and auto correlation is equal to lambda squared plus lambda times sigma T1 minus T2's absolute value, and the autocovariance will be equal to lambda times the impulse of T1 minus T2. And we know it is also actually WSS because its expectation is constant, and the autocorrelation is only depends on the tau. And the fourth will be a semi-random telegraph signal. It is defined as the probability of getting key points in 0t is pk equals to this. It's also related to a Poisson random variables actually, and we will define it as xt equals to 1 when k is even in 0 to t, and it equals to minus 1 when k is odd in 0 to t. So this xt is the semi-random telegraph signal, and the probability of xt equals to 1 is equals to the minus lambda times t squared is power of e times the cosine h lambda t. And here the cosine h is actually a hyperbolic function, and the probability of xt equals to minus 1 will equal to this minus lambda times t's power of e times sine h lambda t. And expectation of it will be equals to minus 2 times lambda times t's power of e. Autocorrelation will be minus 2 times lambdas times the absolute value of tau's power of e, and the autocovariance will be minus 2 times lambda times tau's absolute values power of e minus 2 times lambda times t1 plus t2's power of e. And actually, why it is called a semi-random telegraph signal, because we know it's not an exact random telegraph signal, because because here we know that actually the pxt equals to 1 is not 1 over 2, because we start with positive 1, because here that's the definition of the semi-random telegraph signal, which means x0 will equals to 1. So, and that's why the probability of xt equals to 1's probability will be a little bit larger than 1 over 2, while the probability of xt equals to minus 1 is a little smaller than 1 over 2. And we know that when t goes to infinity, the probability of it will just converge to 1 over 2, and expectation will converge to 0. And so for the random telegraph signal here, actually it will start with -1 or +1 with an equal probability of 1 over 2. So that's what we call random telegraph signal. So the strict definition will be like here is a yt equals to a times xt, where probability of a equals to 1 equals to probability of equals to -1 equals to 1/2, 1/2, and here xt is a semi-random telegraph signal. And finally, the probability of yt equals to 1 will be equal to probability of yt equals to -1 will be equal to 1/2. And expectation will be 0, and the auto correlation will be -2 times lambda times the absolute value of tau over the power of e, and the auto covariance is actually the same value. And actually, you can tell from it is WSS because the expectation of it is a constant 0, and the auto correlation is only related to the tau. And for the random walk next, it defined as when we're tossing a fair coin infinite times, the xt will be equal to xnt capital equals to the ks minus n minus k times s equal to 2k minus n s. And here k equals to the number of tails showed in this infinite times, and n minus k will be the number of heads shown. So here, it is for t is larger or equal to nt and smaller than or equal to n plus 1 times t. And the probability masses will be equal to probability of xnt equals to rs equal to this combination from n and n plus r over 2 and times the 1 over nth power of 2. And the expectation of it is actually 0, and the autocorrelation and autocovariance are both minimal between n and m times the s squared. And for the last one, the Wiener process, it is defined as a limiting process of random walk. So Wt equals to the limitation of xt, where s goes to 0, t goes to 0, and n goes to infinite. And the first order density function Wt will equal to 1 over square of 2 times pi times r times t times the e times the minus omega square over 2 times alpha times t power of e. It's actually normal. No, it's like a normal format. And expectation of it is 0, and the autocorrelation and the autocovariance are both minimal between t1 and t2 times alpha. So that's the end of the first question. So thank you.